Hey everyone, welcome to chapter one of our CompTIA Network Plus. This chapter is an introduction to networking, which means we're looking all about computers, devices, and how software all communicate with each other. We'll look at the types of networks, how they're set up, the hardware that makes them work, and the protocols. So basically, the rules of the road for data. Think of this chapter like meeting the characters in a story before diving into the plot. You'll meet our main players, which are peer to peer and client server models, switches, routers, LANs, WANs, and even the famous OSI model. We'll also talk about safety and troubleshooting so we can keep networks and ourselves running smoothly. So here we go. First, we're going to look at network models. A network's topology describes how all the pieces fit together and how they work as a whole. The physical topology is the actual layout, the cables, the devices, where they're physically placed. It's like the seating chart at a wedding. Logical topology is how things communicate in the software, who gets to talk to who, and how they get permission. This is like the real social interactions at that same wedding. The people at table 3 might still chat with people at table 10, for instance. We also have a network operating system, sometimes abbreviated to NOS in OS. This is a special software that manages the network and controls access. It decides who can use which resources, and it's essential in client server networks. And you can kind of think of NOS as the referee keeping the game fair. So we're going to look at some models here, and the first we're going to look at is a peer-to-peer network, which is often called P2P, where every computer is equal. There's no boss server. Each one manages its own files, its own settings, and its own permissions. These computers in the network are called nodes or hosts. Each node decides for itself who gets to use its resources. Some advantages of P2P is that it's simple to set up because you just connect the machines and go. It's less expensive. There's no need to buy a dedicated server or special software. So think of this as like a potluck dinner. Everyone brings their own dish, decides who can have a serving. It works fine for a small group of friends. Some disadvantages of a peer-to-peer network, and these are some fairly large disadvantages, is it's not scalable. So you adding more devices gets real complicated real fast. There are security issues. There's no central control, so anyone could mess with the wrong settings, and it's not really practical for large installations. Imagine trying to run a company of 200 computers where each one is its own IT department. That is certainly a recipe for confusion. So while it's great for a home network or a small business, peer to peer falls apart in a larger group. So this diagram shows how P2P works. Each computer connects directly to every other computer. There's no central hub, no control point. That means if you want to file from computer A, you have to connect to it directly. There's no single server that stores everything. It's simple, but like a neighborhood without a town hall. It relies on it relies on everyone doing their part, and sometimes they don't do their part. On the other hand, there's a model called the client server network model, and this model really flips the script. Um, in this situation, we have one or more powerful computers, which are called servers, manage the entire network. Okay, they manage resources for the entire network. Resources are managed using some sort of centralized directory database. For example, in a Windows network, it's called a domain, and the tool that manages the domain is called Active Directory or AD. Active Directory is like the master guest list at an exclusive event. It knows every user, what they're allowed to do, and also what they can't do. So in this setup, a user can log in from any computer in the network and get their files and permissions because the server controls it all. This process is run by Active Directory Domain Services, abbreviated it's ADDS. The computer making the request is the client. The advantages of this type of network is that there's centralized user management. One change applies to everyone. The network can be monitored and controlled from one location, and it's much more scalable. You can add hundreds of users without chaos as opposed to what would happen in the peer to peer. If peer to peer is a potluck, client server is a restaurant. One kitchen, one chef, consistent service. So here's a diagram of a typical client server network. You've got multiple client computers all connected to a centralized server in the middle there. Here, the server acts as the brain of the operation, deciding who gets access to which resources, keeping security in check, and making sure no one accidentally deletes the company's entire file library. Network services are the actual benefits of having a network. They include things like web services, hosting websites or internal portals, email, which is sending and receiving messages, file sharing, which is accessing documents from anywhere in the world, remote access, which is logging in from another location, and databases, which is storing and retrieving information. Without all of these services, a network is just a bunch of wires. The network services, are what actually make a network useful. This figure shows an example of a web browser requesting a web page from a web server. The server processes the request and sends the page back to the user. That's how almost every online interaction works, whether it's loading a website, streaming a video, or checking your bank account. Network protocols are like the grammar and vocabulary of networking. They're the agreed upon rules that allow devices to communicate without confusion. And there's two big stars as far as protocols. You've got TCP, which is Transmission Control Protocol. This is like the careful mailman. It makes sure the message gets there intact and in order. If something is missing, it will resend it. And then you have IP, which stands for Internet Protocol, which is the navigator. It makes sure your message gets to the right destination, kind of like the GPS for your data. Together, the TCP and IP form the backbone of the internet. Without them, devices would just be shouting random binary at each other and hoping for the best. When we talk about the TCP IP suite, we mean the entire set of communication rules used by a network operating system, kind of like the official rule book for digital conversations. Some common client-server applications and the protocols they use are on this slide. Web services, which is the HTTP or HTTPS for browsing the internet. Email services include SMTP for sending, POP3 or IMAP for receiving. DNS server, which turns easy to remember names like google.com into an IP address that computers understand. There's database services for storing and retrieving structured data. There's an FTP, which is file transfer protocol. This one's kind of old, but still around. And then remote access, which lets you control a computer from somewhere else. You need to think of these applications as kind of like different types of delivery trucks on the network, all following the rules of the road, which is the TCP IP, but carrying a different load or type of cargo. So this figure shows how email works with these protocols. Notice you've got SMTP, which stands for Simple Mail Transfer Protocol, and that's used to send messages from your email client to the recipient's email server. POP3 or IMAP4 is used by the recipient to retrieve that message. If this were the postal system, the SMTP is you dropping a letter in the mailbox. POP3 or IMAP is your friend opening their mailbox and reading their letter. This diagram shows a LAN, a local area network. This has 5 computers, a network printer, a local printer and scanner, and a central switch that everything connects to. If you look at the physical arrangement here, it's a star typology. Everything runs through that central switch in the middle. If the switch stops working, the whole network stops, just like a roundabout without any exits. A LAN is usually contained in a small space, like a single building. The switch receives data coming into one port, sends it out to the correct port to reach the right device. Think of it like a receptionist who knows exactly where each package needs to go in the office. The network interface card, often abbreviated as NIC, is the physical connector that attaches your device to the network, and it's also sometimes called just the network adapter. So in this situation, if the switch is the receptionist, the NIC is your office door. Without it, you're not part of the network conversation. A LAN can have several switches linked together. The main ways they connect are via a backbone, which is the main conduit that connects network segments, like the central hallway of a building. Bus typology, where switches connected in a single line. The downside to bus topology is that if the line breaks in the middle, traffic can't get through. There's also hybrid typology, which is combining different topologies to suit your needs. And then lastly, hub and spoke topology is when you have one main switch in the middle that connects to multiple smaller switches, like an airline hub system, where it looks like a wheel. You've got the hub in the middle, and the spokes are the peripherals that it's connected to. So this figure shows a hub and spoke technology. The central switch is the hub. That's the one in the middle with the arrow pointing to it. Each spoke connects to another switch, which connects to local devices. It's neat, it's organized, it's easy to grow. Just add another spoke. But if the hub goes down, the main part there, the middle one, every spoke suffers. While switches manage local network, a router manages traffic between different networks. So, for instance, in your house, your router connects your local network to the internet. It figures out the best path for your data, kind of like a GPS that always finds the fastest route. The difference between a switch and a router is that a router belongs to multiple networks and connects them together, and a switch belongs to only one network and routes traffic within it. This figure shows 3 separate LANs connected by a router. The router is like a translator at a meeting. It makes sure each group can talk to the others, even if they don't speak the same network language. Network size can scale out beyond LANs. You have a wide area network, which connects LANs over a large geographical area like the internet. You have a metropolitan area network, which connects LANs within a city. You've got a personal area network, and that's devices within a few feet, like your phone talking to your Bluetooth, or your headphones or AirPods, your watch, your Whoops. And that also includes the body area network, which is wearable tech, uh, like fitness trackers, like the Whoop, or even a smartphone or smartwatch. I'm sorry. So, and then you see that there's these acronyms for each one of those as well. And then you've got storage area network, which is dedicated to moving large amounts of data between storage devices and servers. The OSI model is like the master blueprint for how data travels through a network. OSI stands for Open Systems Interconnection. It breaks down the process into 7 layers, each layer with its own job. This diagram compares it to mailing a letter. You write a letter, which is the application. You put it in an envelope, which is presentation and session. The post office processes and routes it, which is transport, network, and data link. Finally, it's delivered physically, which is the physical layer. Each layer hands the data off to the next one, making sure it gets to where it's going without everyone needing to know all the details. This is a very important model, just an FYI. This second diagram shows how software, protocols, and hardware match up with the OSI layers. The top layers are handled by applications and operating systems. The lower layers are handled by network hardware, like switches, routers, and cables. Think of it like a relay race. Each layer is a runner who carries the baton for a bit before passing it along. So we're going to get into each layer briefly. The application layer is where humans and software meet. This is the interface between two applications on different computers. Examples of this layer are a web browser talking to a web server or an email client talking to an email server. It can also include utility programs like SNMP, which monitors network health. And at this layer, the actual data being sent is called the payload, the real content like the words in your letter. The presentation layer's job is to make sure the data is in the right format for the receiving application. It might reformat, compress, or encrypt the data. An example is when you send an email, your email client can encrypt it here. On the other end, the recipient's system decrypts it before showing it to you. Think of it like translating a letter into a language the recipient can read. The session layer manages the conversation between two applications. It keeps the data stream organized, synced, and handles recovery if something is lost. The session, presentation, and application layers are closely intertwined. Sometimes it's hard to tell where one ends and another begins. A lot of session work happens automatically, like when an application makes an API call to the operating system. An API is like a waiter. It takes your request, delivers it to the kitchen, which is the operating system, and brings back the result. The transport layer moves the payloads from one application to another. The two main transport protocols are TCP, which is Transmission Control Protocol, which is connection oriented. It checks to make sure the data arrives and is complete. And the UDP, which is the User Datagram Protocol, which is connectionless. It sends the data without checking. It's faster, but it's riskier. If TCP is like certified mail where you have to get a receipt, UDP is like tossing a postcard in the mail and hoping it gets there. If the message is too big, TCP breaks it into smaller segments, and the UDP calls them datagrams. Each segment gets a header with control info like port numbers, which tell the system which application the data belongs to. This process of adding headers is called encapsulation, wrapping each piece of data with the instructions needed to deliver it. The network layer moves data from one node to another across multiple networks until it reaches the destination. The star player here is IP, which stands for Internet Protocol. It adds its own header to create a packet, and then it uses an IP address to identify each device. If TCP is the mail service, IP is the address on the envelope that tells the service where to send it. IP does work with other protocols to get the packet where it needs to go. ICMP is an example for diagnostics like the ping command, and ARP finds a device's physical address from its IP address. If a packet is too big, it can be broken into smaller ones. This is called fragmentation. The data link layer connects the network layer to the physical hardware. It puts control information in both a header and a trailer, creating a frame. The address used here is the MAC address, which is the software's unique physical address. Think of it like a device's fingerprint. It's permanent and it's unique to the device. So this is the bottom layer. It's all about moving bits as electrical signals, light pulses, or radio waves. Examples are voltage on copper wires, light through fiber optic cables, and radio signals in Wi-Fi and Bluetooth. It's the literal physical stuff: cables, connectors, and wireless frequencies. So at each layer, the data is called something different. At the application, presentation, and session layer, it's called data or payload. At the transport layer, it's called segment or TCP or datagram UDP. At the network layer, it's called a packet. At the data link layer, it's called frame. And at the physical layer, it's called bits. It's the same information, it's just wrapped differently depending on the layer, like a package that gets put in different containers as it travels. So this diagram traces how a web browser request travels down through the layers on one computer, across the network, and up through the layers on the other computer. Each device along the way interacts with certain layers. For example, a switch only cares about layers 1 and 2, while a router focuses on layer 3. Networks aren't just about data, safety matters too, of course, and fire suppression systems exist at building, room, and rack levels. Data centers need an emergency alert system, portable fire extinguishers, and an emergency power off switch. Fire safety is like backups. You hope you never need it, but you're glad it's there if you do need it. You'll also need to plan for security system behavior during failures, because there will be failures. There's two types of failures. There's a fail open failure where the system allows access during a failure, and then there's a fail close failure where the system denies access during a failure. A safety data sheet, often abbreviated as SDS, explains how to handle hazardous substances like solvents, including first aid, storage, and disposal. Continuing with safety protocols here, electrical and tool safety is regulated by OSHA, which is the Occupational Safety and Health Administration. Some guidelines to use when using power tools is to wear personal protective equipment or PPE, to keep tools in good condition, store them properly, use the right tool for the job, follow instructions, and watch out for trip hazards because cords can take you down real fast. In order to protect yourself against static electricity, or technically called electrostatic discharge, ESD is very important because computers are grounded inside their cases, and static can cause a catastrophic failure, which is total destruction of a component. It can also cause an upset failure, which shortens a component's life. The ESD, the static discharge, is like lightning on a real small scale. It's powerful enough to ruin electronics instantly. Now, to avoid the ESD damage, you can wear an ESD strap and clip it to the chassis of the computer in order to ground yourself. You can touch the case before touching components, and you can also store components in anti-static bags. And always shut the computer down and unplug it before working inside of it, whether it's a computer or switch or anything on the network. Lastly, troubleshooting is something that will happen, and it's like detective work. And there are steps to follow, and they're shown on this slide. You need to identify the problems and its symptoms. You need to establish a theory of what's wrong, and then once you have that, test your theory, and then create a plan to fix what your theory is, implement the solution or escalate it up, verify that it works, prevent it from happening again, and then document everything. Future you will thank you if you document everything. Trust me. So, in conclusion, this chapter introduced the fundamentals of computer networking, covering network models, hardware, protocols, safety, troubleshooting. It explains the differences between peer to peer and client server models. highlighting their advantages, their disadvantages, and practical issues. Key network services and protocols, including TCP/IP, DNS, email, file transfer, are also talked about alongside common hardware like switches, routers, and NICs, as well as network types like LANs, WANs, and MANs. The OSI model was detailed layer by layer, showing how data moves from applications to the physical transmission. The presentation also emphasized safety procedures, including fire suppression, OSHA guidelines, and ESD or static discharge prevention. And it concludes with a 7-step troubleshooting process for diagnosing and resolving network problems. So that is chapter 1. We will see you next time for chapter 2.